As usual, everyone is muted. If you want to ask questions during the talk, we recommend that you do so through the chat, and if necessary, we'll interrupt the speaker, but quite often people are getting answers through the chat as well, so that often simplifies things. The other thing I should say now is that there's the notes are available on the web page. If you're not added to the mailing list, please do so. There are instructions on the web page for that as well. Okay, so let's get straight on. It's a great pleasure to have Agelos Georgakopoulos, who's going to give the first talk this afternoon.
Thank you very much, Alex. It's a great honor for me too, and a great pleasure. Let me try to get my slides. So can everyone see my slides?
Not yet.
Okay. Let me, I guess I need to share my desktop first. Can you see it now? Okay, thanks. Right, so I'm going to report on some recent work with Christoforos Panagiotis about percolation theory. I'll start by reminding you what the model is. I guess most of you have seen this before. On the right-hand side, I have left some space here so that you can put the video, my video there. So I think it works better if you use full screen mode and then put videos in this column, which I will not be using. All right, so what is percolation? We have some underlying graph, let's say the square lattice in the plane. And then for each edge, we flip a p-biased coin and we keep it with probability p. In this case, we say the edge is open, and we remove it with the remaining probability, and in that case, we say the edge is closed. All right, and this model is very simple to define, and there is an important feature about it is the phase transition. This number PC, it so happens that as we increase P from 0 to 1, there comes this PC, below which there are only finite clusters, only finite components, and above which we almost surely have an infinite component. Okay, can you see my screens well? Can you read my handwriting? Thanks. Okay, so this was introduced by physicists as a toy model of statistical mechanics, where you check out how local randomness can cause macroscopic phase transition phenomena similar to those appearing in nature, like magnetization or changing from liquid to solid state. Percolation, it's not itself really a physical model, but it's a good toy model where we can study phase transitions. Mathematicians picked it up quite soon, and there have been many deep results. Also more recently, triggered by a paper of Binyamin and Shuram in the 90s, we've been studying percolation on graphs other than lattices, more exotic graphs, Cayley graphs of groups. We also saw an example in last week's talk by Ron Pellet, where the underlying graph was an arbitrary triangulation. And there we see a very rich interplay between geometry and probability. Okay, I said it's percolation. It's not really a model of modeling nature, but since then there have been discovered many connections to actual physical models like the Ising model. So there is a lot of work and a lot of motivation studying percolation. A helpful distinction to make is in these three regimes. This is very similar to the study of Erdos-Renyi random graphs. We have the subcritical interval, where things tend to be easier. We have the supercritical one, where you have infinite clusters, and the critical is perhaps the hardest of all, although it's hard to compare because we study different questions. So in the critical case, we have, for example, the Fields Medal winning work of Smirnov. Okay, so, but, you know, we have these distinctions into three regimes, but is PC really the only phase transition, or should we further decompose these intervals into smaller ones? Are there further phase transitions? How do we find them? In fact, in the early days of percolation, people introduced a further threshold below which, by definition, below this threshold, we had exponential decay of the cluster size distribution. In other words, the probability that the cluster of the origin has size n decays exponentially in n below that threshold. And it was not known whether this is equal to PC or not for a long time. This was answered in the 80s. Actually, they are equal. There is no other such phase transition there. Below PC, the probability that the cluster of the origin has size n decays exponentially in n. This is, in my opinion, perhaps the most fundamental theorem of percolation theory. And for example, if you want to prove that PC of the square lattice is a half, this is a surprisingly hard theorem, and the bottleneck is exactly this exponential decay. If you know this, then this becomes simpler. And we will see further applications today. All right, so there was no phase transition there, but perhaps there are other phase transitions. And how do we capture them? What is a phase transition? So a natural way to define a point where there is a phase transition is where smoothness of some macroscopic function fails. And let me give you an example of such a function right away. The so-called susceptibility, the expected size of the cluster of the origin, is a nice macroscopic function. Here in this chart over here, I have a science fiction check of chi, the blue line. We know that as you approach PC, it goes to infinity, just because above PC, you have infinite clusters. But so far, we don't know if it's really so smooth as in the picture, or if it has jumps or corners. We don't know if it's smooth or if it could reveal some phase transitions for us. The theorem that I have over here answers this question. It says that chi is actually analytic. So the blue curve is closer to the truth. It's an analytic function. And let me show you how we prove this. I'm going to write down a formula for chi as a series. I'm going to add overall possible clusters of the origin that I could see. So S is a candidate for a cluster of the origin. It's a subgraph containing, my origin will be denoted by O, and it's finite and connected subgraph of G. Okay, and then if I want to capture its expected size, I multiply size of S times the probability that the cluster of the origin actually coincides with this S. So this is by definition an equality. This is the expected size of the cluster of the origin. And for my convenience, I'm going to reorganize this sum by the size of S. I'm going to decompose this sum as follows. S is as before, but it's now forced to have size n. So instead of this S here, I'm going to put this value n there. And I leave the rest of the expression alone. And I can further rewrite this as the probability that the cluster of the origin has size exactly n. Now, I have, let me remark that all these guys are just polynomials, because the probability that C is my cluster can be written as follows. I'm going to write at the top, sorry, I've run out of space. You want all edges inside S to be open. That's why you have a factor 1 of P to the S. And then you want all edges incident with S, but not in S, to be closed. That's why I have this factor 1 minus P to the S. Okay, the point is this is a nice polynomial. So I have expressed the function chi I'm interested in as a series of polynomials. And I know each polynomial is easily an analytic function, but when it's such a series of polynomials analytic? I look into my old dusty books of complex analysis and I find these classics. You have seen them probably a long time ago. We know we have a criterion here for when a series is analytic. You want it to converge uniformly on compact subsets. And when do such functions converge uniformly on a compact subset? We have the Weierstrass M-test as a certificate. You want to have upper bounds for the members of your series, which upper bounds add up to something finite. All right, now let me go back to my previous calculation. It's the same thing. We have these polynomials. Oops, sorry. And we would like to find good upper bounds on them so that the sum of the upper bounds is summable. Okay, so I have this function here, this polynomial, sum of polynomials, the probability that the cluster has size n. Where do I get a nice upper bound? Remember from my earlier slide, we have the exponential decay theorem. It's telling us that this guy decays exponentially in n. And so these bounds, the sum of these bounds is definitely finite. So plugging in this into Weierstrass, we should be done, right? We have our bounds for the M-test. But there is a mistake here. What's the mistake? Weierstrass theorem talk only about complex functions. You cannot, if you restrict them to just real functions, they become false. You want the upper bounds to apply in a complex disk around the point you're interested in. So I am around some point here on the real line, some probability P, and I want an upper bound for this function. Oops. Something happened and I lost my, I'm having some trouble with technology. Hopefully it will come back. Let me just take a minute to try to reconnect my two devices. Okay, it seems to be working again. I'm again here around some point on this line. And I was saying I want a bound for this function. Now, in order to be able to apply Weierstrass theorem, I need to extend this function and also the function chi to complex values. So this might be a bit surprising. P is a probability, chi is a probability, but we extend it to complex values. But this is no problem. What we extend is actually not a probability. What we extend is this polynomial. So it's a technical help for us. it makes perfect sense mathematically. Although intuitively we can't make sense of a complex probability. All right, now we know by the exponential decay theorem that along this line we have good upper bounds, but we want our upper bounds to hold on points that are in the complex plane in order to apply Weierstrass. And do they hold? This is an elementary calculation. You can sit down and do it. How much can the value here differ, the modulus of the value here differ from the value there in this polynomial? Actually, the ratio can be exponentially large in n. So we have an exponential growth multiplied against an exponential decay coming from the probability from the exponential decay theorem. And which of the two wins? Exponential growth against exponential decay. Who wins? Actually, we win, because the exponential growth over here is governed by the radius of this disk. And we can choose that radius to be as small as we wish. We can apply Weierstrass theory to a smaller disk, and there we have smaller exponential growth, and our exponential decay beats it. All right, so this was a sketch of the proof of this theorem. So our function chi is analytic. There are no phase transitions to look there. Let me remark that this is due to Kesten, but we observed that this condition is actually unnecessary. Kesten's original proof was unnecessarily complicated, and by simplifying it, we could extend it to something much more general. I lost it for a second, but it seems it has come back. And we did this remark with Christophoros 2 years ago. And essentially, I have shown you the whole proof. Are there any questions so far before I move on? Okay. So we are now okay in the subcritical regime. We don't expect a phase transition there. Now let's look at the supercritical interval, which is a bit trickier always. Chi is not the most natural function to consider in that case, but we have a very natural other function, the so-called percolation density theta. This is just the probability that the cluster of the origin is infinite. This function is sketched here. Again, this is science fiction. It's of course 0 in the subcritical interval because the cluster is never infinite there, but then it starts rising and eventually converges to 1. All right, and we can again ask, is theta analytic in this branch of theta analytic, or can we find a phase transition there? This was asked by Kesten in the early 80s, and it was back then, I suppose, among the best known open problems of percolation theory. It was then proved that theta is infinitely differentiable. So the problem became less fashionable. And also it was later proved that theta is analytic near enough to 1. So some final sub-branch up there is analytic. But we don't know if it's analytic in the rest of the branch. Okay, now you might ask, if it's infinitely differentiable, what is missing? So let me remind you that the difference between being C-infinity, infinitely differentiable, and analytic is that analyticity means having a convergent Taylor series. You may ask, well, isn't every or almost every function that is infinitely differentiable analytic? Actually depends on whom you ask, but analysts know that in fact the opposite holds. So it's a generic phenomenon in some sense that you can make precise with some topology, almost every infinitely differentiable function is nowhere analytic. You might be a bit surprised. So the question remains, is theta or function theta analytic? Even though we know it's infinity, we don't know that. And this brings up the philosophical question. Okay, so almost all C-infinity functions are analytic, but what about functions that we actually study? In particular, functions coming from studying physical phenomena. Shouldn't they all be analytic as long as they are infinitely differentiable? So Griffiths explored this question. So he introduced models that do not quite come from nature, but almost. So he studied the Ising model for magnetism on percolation clusters. And he observed that there you can actually have failure of analyticity, despite the fact that you are infinitely differentiable. This was called a Griffith singularity. Okay, and now we can ask, if you forget about Ising and just do percolation, this makes the question again interesting. Can percolation alone cause a Griffith singularity? And let me point out that Griffiths studied planar models. So should we study analyticity for planar percolation? And this is what we did with Christophoros, and we were able to prove the analyticity. But before I sketch the proof, let me take a couple of minutes to review something classic. It's an argument of Peierls that gives you an upper bound on PC. So let me review this argument. So we have over here my origin O, and I've run the percolation, and this might be the blue thing is the cluster maybe. So suppose that the cluster of the origin is finite, it's the blue thing. Then the red edges sticking out are all closed. They separate the cluster from infinity. And I can look at them in the dual. And in the dual, they will form a cycle. So Peierls said, let's upper bound the probability that the cluster is finite by studying these cycles, how likely these cycles are to occur. So let's compute a little bit. I have 1 minus theta, which by definition is the probability that the cluster is finite. And I can upper bound this by adding all possible cycles like in this picture. I'm using the union bound. I'm adding overall cycles C. And let's again decompose according to the length of C. So I'll write here the probability that C will occur. In other words, all its edges here in this dual picture, or rather all these red edges are closed. So if my cycle has length n, and each edge I insist on it being closed, I get this expression. All right, and I can rewrite this sum over all n. This is constant. Up here, it doesn't depend on the cycle C. So I'm just multiplying the count of these cycles by the expression on the right. And I have an easy upper bound for Cn. For this graph, since the maximum degree is 4, these are at most, sorry, I lost that picture. So this Cn was at most 3 to the n. And if you do some calculations, it gives you that PC of my square lattice is at most 2/3. Okay. Now, Peierls' argument is very crude. Remember, I had an inequality here. I was counting overall possible cycles. And it's important that I have, it's an inequality because many of those cycles can occur simultaneously. These events are not disjoint. I can have zillions of cycles like that occurring simultaneously, separating my origin from infinity. Maybe this occurs and so on. All right, let's move on. Now we want to prove that the percolation density, this theta, the probability of the cluster of the origin being infinite, that it is an analytic function of P. I'm going to use the same technique as before, extend P to the complex plane and so on. Let's try the same trick. Okay, so I'm going to need some more space. So I'm going to write I'm going to express 1 minus theta, the probability to have finite cluster, as a sum over all possible clusters as before. Earlier, I had an n there because I was looking at the expectation, but now I don't have it. Otherwise, it's the same reasoning. All right, sum over all n, probability that my cluster has size n. And earlier I said by the exponential decay theorem, that thing was decaying exponentially. Now we don't have that, unfortunately. In fact, we know that it decays strictly slower than exponentially, decays like e to the square root of n by a result of Aizenman, De Leon, and Suillard. Okay, so this approach fails. What can we do? Now, let's look at this picture again. This is the cluster of the origin, which we postulate is finite here. It's too big. Let's find something thinner that might decay exponentially. And we will remember the trick from the previous slide. We will look at the interface of the cluster. It's not quite a cycle, but almost. It's an outer planar graph separating my cluster from infinity. And it has closed edges sticking out of it. And this guy, we know that it does decay exponentially. So the probability that this has length, the black thing has length n, decays exponentially in n. Why is that? Again, we look at the dual. The black set is almost as big as this yellow set. And I'm claiming this yellow set decays exponentially. This can be proved by duality. We know that on planar graphs, PC of the dual is 1 minus PC of the primal. And so if we are in the supercritical regime in the primal, as we are in the subcritical regime in the dual. So this cycle is very unlikely to belong. It's exponentially unlikely to belong. Okay, so this gives us the idea. Let's, instead of this sum over the whole cluster, let's write down a sum over, I need more space, over all interfaces. So the interface here in this picture is the black thing. I'm writing the sum over all interfaces with given size n. And then I want to write here the probability that my interface occurs. So I'm tempted to write the probability that this I is actually the interface of the cluster of O. But this is not a nice polynomial. This would, in order to check if this happens, I need to check all edges inside here, the state of all edges inside here. So I could write down that event, but it's not an event that's good to work with. I will not get exponential decay. So instead, I just want to look at the edges of I. So I'm summing of overall candidates for this black set, all possible interfaces that could form the interface of my cluster. And when I say I occurs, I mean that all these black edges are open and all the little red edges sticking out are closed. If such an event happens, I know that my cluster is finite. So I can easily write an inequality here, like I had in the previous slide in Peierls' argument. But an inequality is not good enough for my purposes. I would like to write equality there in order to express my function as a series and do the complex analysis and so on. But do I have this equality? I don't, because it can happen that some interfaces occur simultaneously. Now, let's explore this a bit. Can it really happen? So let's go back to the picture and let's say that some interface occurs. So in particular, all these edges are closed and the black edges are open. And can it happen that some other interface intersecting it also occurs? So this could go inside or outside, doesn't really matter. Okay, the important thing to see here is this edge. So this is part of the first interface. So the first interface insists that it is open. But if you look at the second interface, it's part of its boundaries. So the second interface insists that this edge is closed. So the two interfaces cannot occur simultaneously. Interfaces occur disjointly, at least when they intersect. What can happen, however, is that interfaces are nested in each other. So this interface might be nested inside this one, and the two could occur simultaneously. And this means, again, this puts a question mark on this equality. It doesn't hold as it stands. But what can we do in this case is use the inclusion-exclusion principle. So instead of interfaces, I'm going to work with collections, nested collections of interfaces, which I will call multi-interfaces. And then by using the inclusion-exclusion principle, I do get this equality. Okay, we're making progress. We are not at the end yet. Maybe I'll give you a second to catch your breath and ask questions if you want. I cannot see the question, but if somebody wants to interrupt and tell me. Or should I continue?
So there's a couple of questions that have come up. Is there a generalization of the results P of G plus P of G to the X equals 1 to higher order lattices or in general transitive non-planar graphs?
No, we're talking about planar graphs now.
Planar graphs.
And this is exactly an issue that will make it hard for us to extend the theorem to higher dimensions.
And then two questions about signs, basically. So one saying, don't you need signs? And another saying, do you need minus 1 to the k minus 1?
Exactly, yeah. Sorry, I forgot that. So here I have to put, just because of the inclusion-exclusion, -1 to the number of, to the components of my multi-interfaces. Let me denote like that. So yes, I need signs. Yeah, thank you.
Thanks.
Okay, but the signs do not bother me that much. So I still have an equality there. That's okay. Now, okay, I'm making progress. I've managed to express my function as a series as before. I'm working with interfaces rather than the whole cluster. So I said earlier that interfaces are better because they do have exponential decay. But now perhaps we have lost it that we consider multi-interfaces, collections of them. We need to check that. And here, something that comes into play is the number of ways that I can partition this integer n as a sum of smaller integers, namely the lengths of the interfaces in my multi-interface. And we are lucky here that the possible ways to partition the integer n is sub-exponential in n. So there is this classical theorem of Hardy-Ramanujan that tells us exactly how it grows. It is exponential in square root n. So, but all we need is that it is sub-exponential. A much weaker version of this suffices for our purposes. Okay, then I have some additional combinatorics because I have, if I know the sizes of these nested interfaces, it's not the whole story. I could shift interfaces inside each other, so I get some extra entropy there, but there's not so many ways. We could do some combinatorial calculations to bound that. And again, we could win by using exponential decay in the dual and some elementary complex analysis as before. So to summarize, I gave you a brief sketch just to give you an impression of what kind of ingredients we used. I told you about the complex analysis earlier. It was important that our interfaces cannot intersect. We used the inclusion-exclusion principle, a weak version of Hardy-Ramanujan. For the experts, we also use the BK inequality, but I'll not dwell on that. Okay. So we have now analyticity, at least for planar graphs. We will consider analyticity of theta in higher dimensions later. It becomes much harder just because I don't have the exponential decay. So my notion of interface does generalize. Instead of looking like cycles, my interface look like hypersurfaces. That's not the difficulty. The difficulty is exponential decay in the dual, assuming you can define dual. Anyway, we'll get back to that later. Let me mention that with various subsets of the ingredients that I used before, we could get some further results with Christophoros. We could prove the same result for continuum percolation. We proved analyticity of theta on deterministic or Galton-Watson trees. This had been asked by these people before. In a more exotic setup, we proved analyticity near 1 for every finitely presented Cayley graph, and also near 1 for every non-amenable graph, for example, on hyperbolic tessellations of the plane, like those we saw last week. And there is a fantastic result by Herman and Hatchcroft that came soon after ours, that they got the analyticity all the way down to PC for non-amenable graphs, no planarity here. Okay, so I'm mentioning this because it's again relevant to Ron Pellet's talk. He mentions some conjectures of Beniamini that PC side percolation PC is at most a half. We could almost get that. Instead of the side percolation threshold, we got the bond percolation threshold to be at most a half. by our refined Peierls argument with our new interfaces. All right, I'm going to move on to a different topic. It's a good time to wake up. I'm going to talk about polyominoes now. So a polyomino is a creature like this. Formally, you can define it as a connected induced subgraph of the planar square lattice. And people have been interested for a long time in the counts of polyominoes of size n. They grow quite fast as n grows. They grow exponentially fast. And even for z square, for our standard grid, we don't know their exponential rate of growth. They know they grow exponentially fast, but what's the constant? What's the exponential growth rate? All right, there have been lower and upper bounds. Let me give you a general method that gives you an upper bound. And that works not only for the square lattice, it works on any graph. So it's a classical argument of Kesten that goes like this. So I'm going to write a very similar expression to what I've been writing before. I'll write again, sorry. The probability to be finite, a similar sum as before. You're now used to it. This is just the probability that the cluster of O is exactly my S. Sorry, yeah, that's correct. Now let me just group those things together. I have their count there, and I have Pn. Now they don't all have the same exponent there, but let's pretend we're taking some kind of average. R depending on n, that we will not care much about it because we will just bound it by something that's smaller. So I don't know how much that exponent up there is, but I know it's at most the maximum degree of the graph times n. Because the edges sticking out of any graph, I have at most delta of them for every vertex on the interface, if the maximum degree is delta. Okay, and I know that these numbers grow exponentially in n. I don't know their exponential growth rate, which I denote like this, but there is some number which we are trying to bound, and so the nth term is approximately this by the very definition of alpha. Okay, and this gives us, so on the other side, we know that this is a probability, so it's bounded above by 1. The whole thing is a probability. So by combining this inequality and this inequality, I get in the end an upper bound for the exponential growth rate of polyominoes. You can see in this formula that the bound I get is this. And after some calculations, this gives you this bound, maximum degree times E. Okay, now, this is a very nice, easy argument that gives you an upper bound, but it's not a very good upper bound. We didn't look at all at what our graph is. This works on any graph of maximum degree delta. And the question is, can we refine this with our new theory of interfaces, our new notion of interfaces? we will refine it by not making this crude bound here, but by keeping this R. We are going to elaborate on this R. So this is R is how the ratio of edges sticking out of your cluster as a function of the size of the cluster. Okay, so we're going to try to do better. I'm going to introduce, I'm going to count interfaces now rather than polyominoes. Let me say that the interface form a subfamily of the polyominoes. They're by definition connected subgraphs of my lattice. But so I will write this for interfaces, but I can do the same definition actually for polyominoes. So I'm going to count the number of interfaces of size n and boundary size, by which I mean the number of edges sticking out. Rn, R here is a parameter that also appears on the left-hand side. Now, I'll take R to be an arbitrary real, and generally I will not, for most reals, I will not achieve this exactly. Therefore, okay, this doesn't look good, sorry. I have, let me do something else. I will open up a different, my backup slides and try to present from there. Okay, can you see the slide? Right, I will only use the laser pointer now. So I was writing this sentence. I have interface of size n, boundary size Rn, not exactly Rn. I'm allowing a little window of error, an epsilon window. And the epsilon appears on the left-hand side. So this thing is the number of interfaces, possible interfaces, size n, boundary size R times n, up to an error of epsilon. And in the next line, I define their exponential growth rate. I take lim sup I raised to the power R over n to capture the exponential growth rate. And I take n to infinity. Now I'm getting rid of the window just by taking limit as the window size gets to 0. It's unclear at first sight that this gives me a non-trivial quantity. This limit might be 0, but it doesn't. It captures something, something interesting. And actually, it turns out that the count of the exponential growth rate of all interfaces of my graph coincides with the maximum value over all reals R of this strange function I defined up here. All right, and remember Kesten's argument for before, giving us a rough upper bound on alpha. We can repeat the same, okay, we do something similar, but a bit more tricky, more elaborate, and we obtain this inequality, where these functions f and r are universal functions, don't depend on the graph at all. I'm giving them you right here. We will see a picture in the next slide. Moreover, we have this inequality here, and it becomes equality if and only if, for the particular value of p we're looking at, we have no exponential decay. All right, so this is a bit strange. Up to now, I've been talking about this deterministic function b of r. This is an invariant of your graph with one parameter r the ratio of the edges sticking out over the edges inside. And here I'm talking about percolation. I have the P of the percolation parameter in there. The connection is established through this function. There is a one-to-one correspondence between the parameter space of R and the parameter space of P. And this inequality holds for all values, and it holds with equality whenever exponential decay fails. So I've been talking about interfaces in all this discussion, but all I've said so far applies to polyominoes, the whole cluster, and it has been observed earlier. Okay. Now here is a figure. It sketches the function f of r from before. So f of r has this complicated expression. But when you plot it with Mathematica, for example, you get a surprise. It looks like a straight line. It's not exactly a straight line, but it is almost. Now, the black line is my B of R. This depends on the graph. And it's fictive. I've drawn it by hand. But we know a few things about it. We know it's log concave, for example. And one important thing we know is that okay, we know B of R is always below F, and we know they coincide exactly when there is no exponential decay. For the values of P, that there is no exponential decay in the percolation. And in this picture, I've put them to coincide on this interval. I'm talking now about percolation on ZD with D at least 3. And we know by result of Kesten and Zhang that exponential decay fails in the interval between PC and 1 minus PC. All right. We know, so this here is PC. The values of R here corresponds to values of P after I take my bijections from the previous slide that are in the subcritical regime. So here I am subcritical. And I know that here I have no exponential decay, and therefore this inequality is strict. I'm strictly below F by the exponential decay theorem. Aizenman-Barsky and Menshikov. All right, I've also shown you a branch here in the supercritical regime. How do I know that it is below? With Christophorus, we obtained this result, telling you that if you know the value of B at some point R, this uniquely determines the value at 1 over R. So we somehow mirror at the value of R equals 1. And the values above that 1 uniquely determine the values below 1 and the other way around. So by combining the equation in the box with the exponential decay that we know in the subcritical regime, we deduce the exponential decay in the supercritical regime. Okay, I realize this is a bit hard to follow. I'm mainly trying to give you a flavor. So, okay, before I go to the next slide, remember Kesten's argument gave us an upper bound on alpha by using percolation as a tool. Likewise, we now obtain, a bit surprisingly, a lower bound on alpha if we know the value of PC of a graph. So any upper bound on PC gives us a lower bound on alpha, the exponential growth rate of polyominoes, and the other way around, an upper bound on the growth rate of polyominoes gives us a lower bound on PC. the reason why it's this converse relation is that R is monotone decreasing while F is monotone increasing. Okay, so we have a general way of transferring results between the probabilistic world of percolation, knowing things about PC, and the deterministic world of counts of polyominoes. If you have a bound in one setup, you get a bound in the other. And we managed to exploit this in various setups. In fact, we did very little. We just combined mostly results from the literature. So there is a very recent upper bound on polyominoes in 3 dimensions, and we use this to get this rigorous lower bound on PC in 3 dimensions. The exact value is not known in 3 dimensions. We also looked at what happens asymptotically as D goes to infinity, and we could improve some bound in the literature on the growth rate of polyominoes, which helped us. So this we obtained by combinatorial arguments, and this gave us this bound on PC. Perhaps more interesting is this bullet point. So we used the recent results from of Heidenreich and Matzke that used the lace expansion and deep technique in percolation. They gave us bounds on PC, which we plugged into the previous formula and got bounds on the count of polyominoes, which corroborate equation that has been around. So it was reformulated by these guys recently, while these physicists had obtained it by non-rigorous methods. So we now have this rigorously, and it's conjectured that the converse also holds asymptotically. Okay, I just wanted to briefly mention, this doesn't really follow from the same technique, but there is some similar argument at some point, and Christophoros with Hasselgrave answered this old question of Benjamin and Schramm that, for example, triangulations of the hyperbolic plane, tessellations of the hyperbolic plane have PC strictly smaller than a half. Okay. Now back to here, I have this PR that is about the count of interfaces. So it's relevant for the study of theta. And remember, we have open questions about theta in higher dimensions. A famous question is theta continuous at PC? This is the best known question of percolation theory. And today I was asking, is theta analytic above PC? In particular, is it analytic at this point, 1 minus PC? And when I saw this picture, I thought maybe analyticity fails at this point. Also, perhaps the 2 questions are related because we know that this branch uniquely determines that branch by that formula. So if we know there is a phase transition at this point, should we expect a phase transition at that point as well? So it suggests that perhaps there is a singularity of theta for the value of P corresponding to this point. And for a while we thought maybe that's the case, but then Christophoros came back with a proof that actually theta is analytic in all dimensions. This uses all the ingredients that I mentioned before. So the notions of interfaces extended to higher dimensions, but it is much harder now. We also need the technique of renormalisation. And I guess I'm out of time. If people are interested, I can maybe talk. You can ask me, I can tell you a bit more, but I think I will stop here. So I've been presenting results from 3 papers listing here. And I would like to thank my wife, Georgia, for keeping my son while I'm giving this talk and helping me a lot with the preparation, and also the EU for funding this project in a 5-year project that's about to finish. Okay, thank you very much.
Agelos, thank you for this talk. So if anyone would like to ask questions, please do signal in the chat, and I will in turn unmute people. So first of all, there's a question from Edward Crane. You're appearing twice on my participants list, so I'll unmute both of you.
Okay, only one has a video. So I want to know what you can say about how far you can analytically continue theta in the two-dimensional case. And also, can you say anything about a series expansion around PC on some sector?
So I guess you mean continuing theta on the left of PC, below PC, because above PC, we know it's analytic on the whole branch. And actually, the question was asked, so we considered these questions, and Christophoros told me that you cannot extend analytically at PC, just because if I remember right, the derivative is infinite there.
Yeah, so that's why I was asking whether there's some series expansion in fractional powers of P minus PC.
I don't know.
Okay.
Okay, and we had a question from Peter Winkler as well.
Hi, Agelos. Phone ringing here. Sorry.
Okay.
In the first part, you showed analyticity of the theta function in the supercritical regime. It looks as if that argument should also show analyticity of the expected size of a cluster at the origin, given that it's finite. Is that correct?
Maybe. So we also showed analyticity for a couple of other functions. So I don't remember them all right now. Perhaps Christophoros can answer in the chat.
Looks like he says yes.
Okay. Yeah, I guess it's in the paper.
Yeah. Very nice results, Agelos. Wonderful.
Thank you.
Okay, and we also have next comment from Oliver Redden.
Hello?
Hello. We can hear you.
Yeah. Well, firstly, that's very nice. Thanks. This backward and
Thank
forwards connection with the animals and the percolation thing is very nice. Just a quick comment early on. When you go from the single interface to the multi-interface with exponential decay, I think maybe that step is sort of more or less automatic, because just you can look at the sum over all interfaces of some constant bigger than 1 to the power the size of it, and that's finite if the constant is small enough because of exponential decay. It's like a generating function. And if the generating function for a single interface is finite, then the subsets is finite, because it's just that you're just exponentiating something finite and it's still finite. So, I mean, you did it a different way using a bound on partitions, but it's possible that bit can be expressed more simply.
Okay.
Not a big deal, just a small comment.
Yeah. So yeah, there are. You need to. Possibly you're right. I didn't think about it that way, but let me just point out that there are some complications there. So you need, in order to say that you can use the inclusion-exclusion principle, you need to be able to show that the series is absolutely convergent. So I don't know if that could cause trouble, but okay.
I think it's okay, because you get convergence without the sign, because you're looking at the subset without the sign. Yeah,
okay.
I think.
Yeah,
Right,
possibly there are simpler ways. Yeah. Thanks.
Okay, thank you very much. So if there are no other questions, it just leaves us to, well, first of all, I should say we have a second talk, Cristina Toninelli, coming up at 12:30. But first, I'll unmute everyone and invite you to overwhelm the capabilities of the software by giving a similar